Okay, so we just got done saying in the video, he's like, when I throw a hammer, and so I'm not going to throw a hammer. If you want to go watch him throw a hammer, that's fine. There's a couple pictures here to introduce. We already saw the person walking on the raft as a center of mass example. The throwing of the hammer, well, you can look at either the wrench or the person diving into the water. So it's a little different water example. But here, if you just jump into the water straight, you don't do any kind of tricks, your center of mass, which is for a normal person, is usually in your, oh, I don't know if that was PC for a normal person. For a typical person, I don't know. Anyway, I think of these things now, right? But for a person, your center of mass is in your abdomen region, right? Hips, abdomen, that waist region. And so notice in that first picture, it's the waist dot that follows that parabolic pathway. Y'all listen. Enough talking about the quiz. Focus on the new stuff for the exam, just in 4 classes, okay? But what about the diver who does twists and turns and flips in the air? Well, if there's no external forces, now there is gravity. So gravity is the reason for the projectile motion, right? But you don't see any difference because it's the same force. Your body, your feet, your head rotate about that center of mass. Notice the waist, abdomen area still follows the parabolic pathway. What about this wrench? Did they throw it through the air? I don't think so, because if you threw something through the air, you're going to see a parabolic path, yes? Maybe it's slid, okay, horizontally. This is maybe a top view, but there's some rotation to it. Now, we're not studying rotation till after spring break, but we're just focused on that center of mass piece, okay? And so notice the center of mass of the wrench. It's not in the middle of the wrench, but that's the path that the center of mass follows, a straight line, okay? Okay, well, what if we're dealing with a system? I've got 2 masses on maybe a rod that's negligible mass. So imagine I get that meter stick, very, very light, and I attach 2 heavy masses, 1 at each end. Well, if they're the same mass, well, it's pretty equal and equal distribution of mass, right? And so notice in that picture, your center of mass, and by the way, when you hear me say X marks the spot, I'm referring to the system center of mass. CM is your center of mass subscript. Now, this equation is not on the formula chart. So is AP going to require that you calculate center of mass? No, there's going to be some other, like, not necessarily gut intuition, but using ratios to help, okay? Or y'all, I hope you use this enough that you kind of just muscle memory learn it, right? And so it's not on the formula chart, but you'll see it's not bad. And so what is this equation? The position of the system center of mass is equal, notice the numerator, it's a sum of your mass and positions. So we learned with that demo, it doesn't matter about just having a mass, it matters where you put it. And so M1x1 plus M2x2, and I'm going to say dot, dot, dot. What if you had 3? What if you had 4? What if you had 20, right? And so dot, dot, dot. Divided by a system mass. However many objects you have in your system, it's the total mass, okay? And so here they're talking about if they're equal mass, the factor of M, or the variable M cancels out, but that 2 in the denominator doesn't. And so basically it's going to be in the dead center, right? What if it's not symmetrical? So I'm going to add, this problem is somewhere on another slide, but I'm going to do it now. And so add to it, hopefully you can find some space, just a little bit. What if I've got a 2M mass on a light rod? And by the way, we say the rod that connects these two typically is massless. You will see problems where it does have mass, and like our meter stick, you have to make sure you notice, is it uniform or is it not? Okay. But here we'll say the rod connecting these two is massless. So it's not really part of our system. It's just so they don't float in the middle of the air. And so where is the system's center of mass? Well, that M1x1 plus M2x2 divided by the system mass. Now, I am going to tell you to get a position, you need a reference point, right? Position is a vector. Center of mass is a vector. And so we need to decide where is the 0 point. Well, I've decided today we're just going to stay in the positive quadrant. And so I'm going to say that the most left spot is our 0 meters. Meaning the most right location, I'll just say is L. No number really, just it's the length of whatever, okay? Sometimes the problems will define where 0 is, but if it doesn't, put it where is most convenient. It's convenient to make it, on the left so you don't have any negative values. And so I believe we should be able to solve now. And so M1, does it matter which one's M1 or M2? No, I typically go left to right. And that'll bother some of you because the coefficients are backwards. Tomato, tomato. We should get the same answer. And so if I call ball on the left 1, I would say 2M times the position, well, it's at the 0 meter mark, so that part's going to 0 out. How convenient. Plus 1M, and what's its position? L, divided by your system mass, 2M plus 1M is 3M. And so what's going to happen here? M over M cancels out. And what is your system's center of mass position? 1/3 L from 0, right? 1/3 L from 0. And so I'd come in here, maybe look at it as 3 sections, right? 1/3, 2/3. And so at 1/3 L, X marks the spot. X marks the spot. That's where you would put your finger to balance these objects, this system. Yes? Well, if they don't give you the equation, what's this other way to solve for it? So here's the ratio way to solve for it. Are you ready? You're basically doing the same thing, but AP typically does keep with nice ratios when it comes to these problems. So our mass is in a 2-to-1 ratio. Maybe tomorrow it's a 3-to-1, a 4-to-1, right? You still have to ask yourself, well, what's the total mass, system mass? Well, it's 3M. So watch this, 2M over 3M, this is 2/3 of your system mass, where your single M is 1/3 your system mass. So we're doing some kind of proportion with the individual mass to the total mass, right? Your position, your center of mass position is going to have a distance inverse relationship. And so your 2/3 mass, you're going to have 1/3 the total length available or total distance. And then the distance from your smaller mass to your system center of mass will be 2/3 the total distance. So think of your mass in terms of 3s, think of your distance in terms of 3s, and to balance this, you need an inverse relationship between mass and distance. Does the proportion make sense? What if it was 3M and 1M separated by L? Let's just strictly do the proportion. Total mass is 4m. So I have 3/4 the system mass over here. So I'll have 1/4 the distance total, or L. 1m is 1/4 the system mass. So I'll have 3/4 the total distance, or L. And so imagine L split up into fourths, where X marks the spot, where? Well, it's 1/4 of the way from your heavier mass. Does the ratio make sense? That's probably what you'll be doing in 90-something days on the AP exam, okay? Or they'll give it to you as maybe, definitely with rotation, you'll consider center of mass. But in terms of figuring out where is it for your system, probably nice numbers, probably ratios are going to be your best bet. Or know the equation, calculate it out. Okay. Now, what about an uneven, an unproportional, non-symmetric, oblong, whatever, asymmetrical type of object, okay? 3 thin rods, each of length L, are arranged in an inverted U. So it's kind of an odd-shaped boomerang in my mind. 2 rods on the arms, left and right, have a mass M. And the third rod at the top has a mass of 3m. Where is the center of mass for the assembly, for the system? And so X marks the spot. Where's it going to be? Well, this one's different. It's two-dimensional. It's not just a left-right business or an up-down business. I've got 2 to figure out, because it's not only a left-right system, it's an up-down. So this is 2D. We're going to do the system center of mass twice. Once with horizontal information, and then once with vertical information. So using the equation, but first we need to identify our 0 point. And again, I said today we'll just keep in quadrant 1. So all the rods are L in length. So your max vertical can be designated as a position L. The lowest would be 0. In the X direction, the most left will be 0. And the furthest horizontal position would be L. Everybody good? Now, the rod itself, if you think about that meter stick that I first started, just a meter stick, assuming these rods are uniform in shape and mass distribution, each of them has their own center of mass. An object alone has its own. So each meter stick or each rod would have its own center of mass in the middle. But that's not what they're asking. They're asking about for the system. And so to calculate it, let's use each rod's mass and position, horizontal first. And so M1, we'll call this one on the left. M2, we'll call the one on the right. And I'll keep with the coefficient. M3 will make the 3m. And so M1 is just 1m. What's its horizontal position of the individual center of mass? Just looking at rod number 1, what's the X reading of its individual center of mass? 0. If you were to look at it as a point on a graph, that point would have a 0 reading. And so it's got a 0 position in the horizontal, which times a mass, well, that's 0. Plus M2, I labeled as the rod on the right. It's 1m. What's its center of mass individually? Horizontal position. L plus 3m And what's its individual center of mass horizontal distance? 1/2 L. All over a system mass of 1m plus 1m plus 3m, 5m. And so 3 divided by 2, this last one is 1.5 ml plus 1 ml gives us what numerator? Divided by 5 ml, what happens to the mass variable? Cancels out. Now, I'm sorry. I was about to say L's don't cancel out because I shouldn't have put it there in the denominator. And so now the horizontal position of our system center of mass will be found at 1/2 L. And so if we go back to the picture, that 1/2 L location, well, this is going to be the region of our system center of mass. And if you look at it, doesn't that make sense? Isn't it left, right, symmetrical? Mirror image? So symmetry, in a little different sense, should be your friend. You may not have needed to do that calculation if you're like, oh, the left side, right side, cut it in half, right? But the top bottom, we should do the vertical because it's not so much symmetrical. And so now I'm going to switch to a Y position just to note vertical positions. Same strategy, 1m. Now the question is, looking at that left rod, its individual center of mass is at what vertical position? 1/2 L. Plus, go to the right rod, its individual center of mass is at what vertical position? 1/2 L, so 1m times 1/2 L. And then M3 is a mass of 3m. What, for its individual center of mass, what's its vertical position? L. All over 5m again. And so when we simplify the numerator, what's 3ml plus 1/2 ml plus 1/2 ml? 4ml divided by 5m. Mass cancels. We're looking at a vertical system center of mass position of 4/5 L, or you could say 0.8 L. It's not going to be in the middle, but if we estimate here, 3/4, and so it's a little above. X marks the spot for your system center of mass. Can we touch this spot to balance? No, you can't always touch it. You can't always see it. In a situation like this, how you would see this center of mass is if we kind of threw it like a boomerang. It would rotate about this location, but you can't actually touch it or see it. And so that's one of the struggles with center of mass. And you saw the last video, he put a ball in between the two carts and used a black light so that you could isolate what you were looking at and focus on what would be the system center of mass. But you don't always see it or touch it, okay? But it's there. Questions on a 2D center of mass. All right, next page. We got, this one was the one 2-to-1 ratio. I've already done that. So we'll move on to this top right one. Here we're going to get kind of into those collisions. This is the anti-collision. It's an explosion. A 3-kilogram object is launched into the air. Now imagine if it didn't blow up. Where would this 3-kilogram object land if it doesn't blow up? Neglecting air resistance, it's a projectile. It was launched from something, right? It would land, oops, right here, right? If it didn't blow up. And so that's what the projectile pathway is showing us. But at the peak, it's going to blow apart into a 1 kilogram piece and a 2 kilogram piece, which initially follow horizontal trajectories. So right after the explosion, they just go left, right, out. But they still have that parabolic motion individually, but we're going to look at it as a system. The 2 kilogram piece lands 10 meters from where it would have landed had it not exploded. Where does the 1 kilogram piece land? And so you could do the equation, but let's do the ratio. It starts out as a 3 kilogram, right? And so our 2 kilogram is a 2-to-1 ratio, right? It's got 2/3 the total mass. And so it's going to have 1/3 the total distance. And so our 1 kilogram object has 1/3 the total mass. So what fraction of the total distance is it going to have? It's an inverse relationship between the position and mass. If I've got 1/3 the system mass, I'll have hello? If I have 1/3 the total mass right here with the 1 kilogram, what percentage of the total distance will I have? 2/3, or we can go on an answer. Okay, so we'll have 2/3 the total distance. Now they didn't give me the total distance, but if I know 1/3 is 10, 2/3 will be 20 meters. Okay, total distance, a separation would be 30 meters. Is the ratio make sense? Okay. Okay. Bottom left, we've got a center of mass with 4 objects. So that's the ... It's not any harder. It's just a little extra writing and a little extra time. And so calculate and mark the center of mass of the system shown in the diagram. Now this one does define the 0 meter location. It's that very middle. And if you notice, we have a 3 kilogram, 2 kilogram on the left, a 1 kilogram, 4 kilogram on the right. So if you think too quickly, you're like 5 on the left, 5 on the right. Put your finger on the 0 meter mark and it should balance. True or false? What are you ignoring? The position, right? It's not about total left mass and total right mass. It's about their positions. They're not in the same spots. And so let's get some more practice with that equation. X center of mass for the system. And I'm going to go left to right for my M1 sequential order. So our 3 kilogram is at what position? So they've defined 0. So count it over. 1, 2, 3, 4, 5. 1, 2, 3, 4. This is 10 to the left. Position is a vector, so I have to say -10. Don't believe the darkened lines. Count it out. Plus, our 2 kilogram is 2 to the left, so -2 position. Plus our 1 kilogram is 1, 2, 3, 4 to the right. And then our 4 kilogram is 5, 6, 7, 8, 9, 10 to the right. And don't forget to divide by the total system mass, which should be 10. And so we get -30 minus 4 plus 4. So those are going to get rid of each other. Plus 40 all over 10. So we get a positive 10 over 10, or 1 meter is our system center of mass. So X marks the spot right there. So if they were all connected with a long rod, you would put your finger at the X marks the spot and it should balance. Or if you rotate it, threw it through the air, that's the spot that would follow the trajectory. Good deal with basics? Okay. On the next page, start to get into this collision idea. And so find page 11. This, luckily for us, the masses are going to be the same, but that's not where it's going on this problem. Remember, earlier, Newton's laws, kinematics, it all works for individual objects and for systems. Find the center of mass position and velocity, that's new, at time equals 0. So the pictures we're looking at are the initial velocities and positions of each object. Notice they already define the 0 meter mark. For your left box, these two are going to go towards each other at different speeds, velocities, positive 10 and negative 4. And they start 28 meters apart. And so to find that position, well, they're equal mass. So what would be the position? 14. So this is 14 meters. And so dead center, X marks the spot. But here's the thing, our system is not at rest, our system is moving. Yeah, that imaginary spot is moving. And so VCM, we're going to find the exact same way, M1V1 plus M2V2 divided by our system mass. Wait, M times V, that's momentum. Look at this. This is basically a momentum calculation, yes? We're using it as the system center of mass. And so M15, it's moving positive 10, plus another 5, it's moving negative 4, divided by the total mass of 10. And so we get 50 minus 20, or 30 on top, divided by 10. VCM is equal to 3 meters per second to the right. And so that imaginary X marks the spot is moving. It's moving because your system is initially moving. That's weird. After 3 seconds, where is that X marks the spot? Well, we can do that same kinematics that we did for a point particle, but do it for this imaginary X marks the spot. All your kinematics is still true, right? Now, first we have to ask ourselves, did they mention any external forces? There's no mention of it, so the only safe assumption is that net external force on the system is 0. Okay, on the system, I'm not talking about when they collide, the net external force. So this is the water of the surfboard, the water of the canoe. And so for that, the acceleration of the system is going to be 0. So what's going to be true about our velocity? It's going to be constant. So this center of mass, constant velocity, well, that's displacement over time. And so we know displacement is final position minus initial position, and it's the final that we're trying to solve for. And so the velocity of X marks the spot is a positive 3. We're trying to find the final position. It started at 14, divided by 3 seconds. What's the final position of our system's center of mass? 3 times 3 plus 14, 23. So we just did kinematics with an imaginary point. One more. At 3 seconds, what if my first object has made it to 15 meters? Where is X2? Y'all, we're doing the same equation, just solving for something different. And we're using final positions now. We know the final position of the center of mass is 23. We know 5 kilograms of the first block has made it to 15. And we're looking for the final position of our second block. System mass didn't change. And so solve for me. Where will object 2 be after 3 seconds? Get me an answer. So 230 minus 75 divided by 5. When you get me an answer, we can call it quits. 41, 31, and positive, right? Okay. So hopefully you're catching the idea of this center of mass of a system. Newton's laws still apply. We'll continue the center of mass practice next class.